So welcome to this fourth lecture now. In the last lectures we have seen some guidelines about how do we design real life reactors, what considerations come into picture, and in the last lecture more specifically about what do we do for exothermic reactions, what kind of considerations come into picture and how that influences our choice of reactor geometry, uh, even if the residence time is the same. What we are going to look at now are some more aspects about uh, adiabatic processes and diabatic processes, diabatic reactors. We are going to look at more specifically in this lecture. We are going to look at more about uh, continuous well mixed reactors when they are being used for exothermic reactions, either in adiabatic mode and diabatic mode, but we'll consider both steady state as well as unsteady state. So just to refresh your memory, this is where we are in our course. We are on this second topic of our real life reactors. To help you get into the frame of this lecture, uh, some questions for you to think about and recollect from the previous class. First is derive an expression for maximum adiabatic temperature rise in a continuous reactor. So this could be a well mixed or it could be a plug flow, either way. Second is derive an expression for temperature difference between center and wall for a tubular plug flow reactor, between the center temperature at the center line of the reactor and wall of the reactor for a let's say for a reactor where there is a it could be adiabatic, or we could think of it as a for a situation where heat is being transferred to outside. So calculate that and think about what are the implications of that in terms of reactor operation. Is the following statement correct? That's the next question. The statement is, for an exothermic reaction conducted in an adiabatic manner at steady state, the conversion in a well mixed reactor will be higher than a plug flow reactor for the same residence time in both the reactors. Think about this statement, think whether it will be a right, whether this statement is correct or incorrect, and then once you decide whether it is correct or incorrect, think about what are the reasons. Go back to previous lecture, study that, do calculations, and then check whether this statement is correct or incorrect. What we are going to do in this lecture more specifically is we are going to focus more on adiabatic well mixed reactors, and we are going to look at steady state first and we will look at the unsteady state afterwards towards the later half of this lecture. Okay, so first of all, what we are going to assume, we are going to do this analysis for first order exothermic reaction where rate constant will be given as K0 exponent of e raised to minus E by RT. So E is the energy of activation and heat of reaction is minus delta H. So it's an adiabatic, it's an exothermic reaction. Heat of reaction is negative. I've just written delta H, but in reality it is minus delta H. Okay. Let's assume that the properties such as density, specific heat, these are constant numbers. They don't change with temperature. Okay. So this is the reactor. Let's say there is a flow rate coming in. F is the flow rate, CAI is the inlet concentration, TI is the inlet temperature. Well mixed reactor, continuous and steady state. So well mixed means whatever is the concentration inside and outside and going out from the reactor is the same. So flow rate going out is F, outlet concentration is Ca out O, CaO if you like, and outlet temperature is T0. And because it is well mixed, concentration everywhere inside is Ca0, temperature everywhere inside is T0. And remember, this is an exothermic reaction, therefore T0 will be higher than Ti. Heat is generated by way of reaction. The whole reaction mass will get heated up to a higher temperature, and that temperature is constant because it is a well mixed reactor. What I want you to do is plot conversion in the reactor XA as a function of residence time in the reactor, tau. Also plot this temperature T0 out, T out, To if you like, as a function of residence time tau. Okay. Just to get you started, we have written material and energy balance equations in the last class as well. Try writing them again without seeing the previous lecture. But if you have difficulties, you can always go back and see the previous lecture. We have already written the material and energy balance equations. Okay, so pause the video, write these equations for yourself, and calculate how this XA and T naught, T out if you like, To will vary with respect to tau. Okay, pause the video. Okay, here is some solution. We have written this in the previous class. If I write material balance, whatever is coming in to this reactor minus what goes out must be equal to what is reacted. Okay, so flow rate, what comes in is flow rate multiplied by concentration at the entry, CAI, minus what goes out, flow rate multiplied by concentration at the outlet, whatever is going out, CAO. Reacted is first order reaction, so KCAO is the rate of reaction, so that's KCO is per unit volume multiplied by volume of reactor, so that will be the moles, kilomoles reacting per unit time. In minus out is equal to reacted. Material balance, we have done this some long back in our undergraduate course. Only thing that is different now is this K is dependent on the temperature, and in this temperature also we don't know. So this K we can write as K0 e raised to minus E by RTO, Ca naught and V. And we will write this in dimensionless form because we want conversion. So we will write XA as the conversion of A as 1 minus CAO by CAI. So if you substitute this, you will get one equation, XA is equal to K naught e raised to minus E by RT at the outlet TO into 1 minus XA into tau. Enthalpy balance, again we have written this in the last class, but just to help you, whatever enthalpy coming in plus what is generated minus what is going out. Right now we are saying this is an adiabatic well mixed reactor, so no heat is transferred to the cooling medium, no heat is transferred there. So whatever enthalpy comes in plus what is generated is what is going out. So enthalpy coming in is flow rate multiplied by rho CPTI. Recall, this rho CPTI is nothing but enthalpy per unit volume multiplied by volumetric flow rate is the rate at which enthalpy comes in, joules per second, kilocalories per second if you like. What is generated? What is generated is by way of exothermic reaction. What is it? What is the rate of generation? It is rate of reaction, rate at which the molecules of A or moles of A disappear, multiplied by delta H, heat of reaction. So this in plus what is generated, remember heat of reaction is negative, so we are saying minus delta H, that's the generation term. Exothermic reaction, delta H is negative, that's why we have this minus delta H. Take care of units. We could have this concentration in kilomoles per meter cube. Delta H is in terms of given usually in terms of kilocalories per gram mole. So take care of the units. We have been doing that since last lecture. Equal to what enthalpy goes out? Rho CPT out is the enthalpy per unit volume multiplied by volumetric flow rate. So that will give you the rate at which enthalpy goes out. So if you rearrange this expression, you can write it in terms of TO, T out minus T in is equal to K naught exponent of minus E by RT naught 1 minus XA CAI delta H rho Cp and tau. Okay. Now last class what we have seen is what is the maximum temperature at the outlet. We have seen this, that was a part of revision. Recall this first part of that revision, maximum temperature rise. Okay, or if you like we can combine these two equations and say that T naught minus Ti would be XA CAI delta H by rho Cp. How we are saying that? Look at this expression, look at the first expression. Just one second, let me take a pen. Yeah, look at this expression. Look at this expression, K naught e raised to minus E by RT naught XA and tau. This is the same thing that appears here, K naught exponent of minus E by RT 1 minus XA tau. It is the same thing that appears here. So I can substitute the left hand side of this, that is XA. So T naught minus Ti would be XA CAI delta H by rho Cp. That's what we have written here. Right? This is that equation. What is the maximum temperature rise that will happen? That will happen when all of A is converted, which means when XA is 1. That is the maximum temperature rise. Maximum. That's why we are writing T naught minus Ti maximum. Okay. So that maximum delta T temperature rise is CAI minus delta H by rho Cp. Use this definition of delta H max to make this equation, the previous equation, dimensionless. So we can write T naught minus Ti. This was our equation on the previous page. All I have done is expressed CAI minus delta H by rho Cp in terms of delta T max. So that delta T max has appeared here. See? Okay, I can divide now. T naught minus Ti divided by delta T max is equal to K naught exponent of minus E by R T naught 1 minus XA into tau. So this I can define as a dimensionless temperature rise. So we are going to write this as theta. So theta is our actual T naught minus Ti divided by this delta T max. Okay. So theta would be K naught e raised to minus E by R T naught 1 minus XA into tau. And of course we have our first equation from material balance. XA is K naught e raised to minus E by R T naught 1 minus XA into tau. And these two, if you take together, you will find that theta is nothing but XA. Okay. So now we can solve any one of this equation and theta equal to XA equation and get a expression for how theta or XA change with respect to tau. Okay. Remember, this T naught, that is actually we don't know that value, right? So this T naught we can also write in terms of theta as Ti plus delta T max into theta. This T naught we are writing from here, right? Now in this equation, what are the things that we know? K0 we know, E we know, R we know, inlet temperature we know, delta T max we can calculate. Once I know the exothermicity, once I know physical properties, once I know the inlet concentration, delta T max can be calculated, right? So we have unknowns. Let's put that in some other color. Unknown theta, 1 minus theta and tau. So what I want you to find out is, what I'm asking you to plot is here. Plot temperature T naught as a function of residence time. So you can take different values of residence time tau and solve this equation for theta. Is that a good idea? So I can take different values of tau. I can take different values of tau and solve for theta. So I will have to solve a nonlinear algebraic equation. You realize? Another option is I can assume different values of theta, assume different theta and solve for tau. It is the same way. I want a relationship between theta and tau. How I get that relationship from this equation is immaterial. I can take some value of tau and solve a nonlinear equation for theta, or I can take different values of theta and solve a linear equation for tau. It is linear in tau, but it is nonlinear in theta. Think about this. So now we can solve. So what we will do is take different values of theta, solve for tau using this expression, and of course XA is straight away just the same as theta. Okay. What values of theta you will take? What is the variation in theta? How much does theta vary? Theta can be 0 if heat of reaction is 0. So maximum variation for theta is going to go from 0 to 1. We have made theta dimensionless. We have made temperature dimensionless by defining the temperature change at any value of delta H or any value of conversion by what would be the maximum possible temperature rise if everything got converted. Right? So maximum value of theta can be 1 when XA is 1, everything gets converted. Right? Minimum value of theta would be 0 when no conversion happens, or if delta H is 0. Right? Okay, so let's do this. Do this for yourself. Pause the video, do this for yourself, and actually plot for yourself. What you will find, so these are just the same equations. Now you will need some values for plotting. So you can take these values. You can take these values for plotting. So rho is 1000 kg per meter cube, Cp 0.96, typically like water. E by R 15,000 kilocalories per gram mole. Delta H is minus 52 kilocalories per gram mole. K at 298 Kelvin is 0.004 minute inverse. Right? So use this and E by R to calculate our value of K0. Okay. Ca in 2 kilomoles per meter cube, temperature in 298 Kelvin. So use these values and solve these equations. Get a graph or generate use a spreadsheet, Excel or something like that, or whatever is your favorite spreadsheet software. Plot a graph of how theta changes with tau, and plot a graph of how XA conversion of A changes with tau. Okay, plot this for yourself. Pause and plot this for yourself. Once you have plotted, then only go forward. Here is what you will find. If you plot residence time in minutes on x-axis versus theta on y-axis, this is how the graph will look like for these values. These values. And theta and xa are same, right? So whether I plot theta or whether I plot xa, it is one and the same thing. So xa is dimensionless conversion, theta is like dimensionless conversion, but in terms of temperature. And once I calculate theta, I can always use this definition. I can always use this definition of temperature. Where was that definition of our theta? This was our definition of theta. Once I know theta, I can always calculate the outlet temperature, because inlet temperature we know, delta T max we know. We can always calculate the outlet temperature. So you can plot now outlet temperature versus residence time. Advantage of doing it in dimensionless form is that we can extend this analysis to any reaction, whatever be the delta H, whatever be the rho, whatever be the Cp, whatever be the Ca inlet concentration, right? The moment we write into dimensionless concentration, it becomes independent of these local values of variable. Today, for this particular problem, CAI is 2. Tomorrow, CAI could be 5. Or delta H is, in this particular case, some value is given to you, 52 kilocalories per gram mole. But in terms of theta versus tau, it is applicable for all values of delta H. Correspondingly, the actual temperature will change. If it is more exothermic, outlet temperature will be still higher. If it is less exothermic, outlet temperature will be lower than this. But in terms of theta, we will have a unique solution. That's the advantage of writing in terms of dimensionless numbers. So what I want you to think about is, what do these graphs tell us? Note down, make notes in your notebook. What points can you come out with based on this graph? What do you think? If this was a real reactor, what does it tell you? What does this graph tell you? Either temperature or theta. First thing is, for a given tau, outlet temperature and XA can have multiple values. You see, if residence time is, let's say, 1 minute, theta can be close to 0, theta can be 0.35 or something like that, or theta can be 0.99. In terms of temperature, if you like, if residence time is like 4 minutes, 5 minutes, somewhere here, outlet temperature can be something like 300 Kelvin, outlet temperature can be 325 Kelvin, somewhere here, outlet temperature can be close to 405 Kelvin, right? That means there are multiple steady states. Multiple steady states. For a given value of tau, I could have a reactor operating at any of these three values, because these values, they satisfy our equations. Their values are coming from these equations. So I have reactor can operate either with these any of these three values. Okay. The lowermost state or lowermost steady state is called as extinguished state. The highest steady state is called as ignited steady state. Why? Because temperature is so high, practically 100% conversion. That's why it is called as ignited, because temperature rise is sudden. All of a sudden temperature is rising from the inlet temperature to 405, as if there is the ignition. Lowermost is called extinguished because hardly any conversion has happened. Practically nothing has happened, as if the reaction is extinguished. Nothing is happening. Zero, practically zero conversion. Practically very little, maybe 1 or 2 degree rise in temperature, as if there is no reaction happening, as if the reaction is extinguished. That's why the lower steady state is called as extinguished steady state. Higher steady state value is called as, or the high is called as ignited steady state. But you see, sometimes I may not have three steady states always. For, let's say, for one particular case, so if my residence time is something like this, I may have only one steady state value somewhere here. Or a residence time something like this, I may have only one steady state value. So these multiple steady states exist only in this window. This window. Anything below, I have only one steady state, which is practically zero. Anything above, I have only one steady state, which is practically 100% conversion. Okay. You can read this paper. This paper talks about all these things. Actually, they have actually done experiments and measured these values for some reaction. Okay. We'll talk a little bit about stability of these steady states as we go along. But the reason I'm bringing this point is you could have very dramatic reactor behavior when we change values of residence time. For example, imagine that you are operating a reactor. Imagine that you are operating a reactor at, let's say, 5 minutes residence time, or 6 minutes or 8 minutes residence time, somewhere here, and you are operating here. Now, by some chance, if the flow rate reduces, residence time will go up, or you want higher conversion, you will try to maintain higher residence time. So let's say your residence time goes up from 8 minutes to, say, 11 minutes, somewhere here, or 12 minutes, 15 minutes, something like that. Your conversion straight away jumps from 20-25% conversion or 5-10% conversion to straight away 90-95 or 99% conversion. So if you are saying this is, say, something like 8 minutes and this is like 15 minutes, your conversion is jumping from here to here straight. It is a jump from, let's say, 10% conversion to 99% conversion, 100% conversion. So you have to be careful when you are changing residence time, either accidentally when flow rates are changing, maybe pump failure or something like that, or you are deliberately changing residence time in order to get higher conversion. How sensitive the reaction is in this temperature, in this value, in these conditions, where a small change in residence time can lead to a dramatic change in the value of conversion or value of temperature. That's why this higher state is called as ignited state. Or same way, if you want, let's say you are reducing residence time, either pump flow rate has gone up, or you deliberately want less reactions, so you are trying to reduce the residence time by increasing the flow rate and things like that. Your conversion will drop from 99% to something like 5%, 10%. So much sensitivity is there, and that's why reactor process control for reactions becomes so much more critical. You have to understand all these things and take into account when you design control systems for such reactors, that your reactors can exhibit extreme sensitivity to small changes in residence time or small changes in flow rate. Okay, let's go little forward. Okay, try to understand all these things, try to think what all these values mean. Okay, same thing will happen if you are operating reactor here. Let's say somewhere here you are operating, you are getting practically 99% or 95% conversion. Say somewhere here you are operating, you are having a 95% conversion. You reduce the residence time little bit, suddenly your conversion drops to 0, right? Your temperature drops to practically the inlet value. Okay, okay, let's go forward. um, all these things you can solve for yourself when you use a spreadsheet to solve all these things. Let me just show you uh, what I'm trying to say. So if you are saying, let's say this is your, these are the energy balance equations, that's what you have, that's what are plotted here. This is a graph of theta versus residence time, and this is a graph of conversion versus residence time, and this is a graph of outlet temperature versus residence time. Look at all these graphs. What I'm going to do is I have already written this solution. I have already written this solution. I have written it in Excel. So what I'm going to do is change the values of various parameters. So this is my value of E by R. Look at what happens to this graph as I change E by R, or what happens to this graph as I change delta H. Let's say we increase delta H, right? You see how dramatically things have changed. Let's go back a little bit, right? Let's reduce delta H. So you see, if you reduce delta H, this sigmoidal behavior, or the window where I get 3 steady states or multiple steady state, that window has reduced. And as I increase delta H, the window where I get multiple steady states has increased, has widened. Okay, same for E by R. E by R tells us how sensitive the reaction is to temperature. If I reduce E by R, the reaction becomes less sensitive to temperature. The window of multiple steady states will reduce. See, it has reduced. Practically this window is practically, it has gone. Practically it is a unique solution. And if I increase del E by R, the window will go up even more. So you can use spreadsheets to understand all these behavior. You can put these formulae and you can calculate all these things, and then it is very easy to understand the behavior of these systems. Let's go forward. Okay, do this for yourself, do that spreadsheet also for yourself. Only then you will be able to understand. Only when you plot and you play around with the values of E by R and delta H, you will be able to appreciate all these things better. Let's have a closer look at energy balance. We will talk about this energy balance from a point of view of our multiple steady states, as to when we will get multiple steady states, when we will get single unique steady state. Just I'm going to plot 2-3 different lines on this graph, and then we can come back. So I have, let's say here, if my residence time is something like, let's say 0.08 minutes, 0.1 minutes, I get 3 steady states. Here also I get 3 steady states. But beyond this point, beyond 10 minutes, 12 minutes, 15 minutes, I get 1 steady state. Or below this 0.01 minutes residence time, I get only 1 steady state. So we are going to look at, let's say, any residence time, and we are going to look at all these 3 steady states. Why these 3 steady states happen? is because it's an exothermic reaction. It's a nonlinear equation. Nonlinear equation. And in nonlinear equation, it can have multiple solutions, and therefore we could get multiple steady states only in some region of residence time. We are going to look at three steady states, either in terms of temperature or in terms of conversion. In terms of why these are happening, it is happening because my heat removal rate by way of the flow rate. So heat, if you can think of heat removal rate as in minus out as heat removal rate. So F rho Cp T naught minus F rho Cp Ti. So this is our heat removal rate, if you like. Enthalpy is being taken out by the flow, and this is enthalpy generation rate. Enthalpy generation, and this is our heat removal by flow. So interplay of these two parameters, heat generation and heat removal by flow, that gives rise to these multiple steady states. So what we will do is we will look at these individual terms, heat generation term and heat removal term, in a little bit more detail for different values of residence time, and try to look at the stability of these steady state. Which of these three steady state is stable and which of these three steady states are unstable. Okay, this was our energy balance equation, this was our material balance equation, and this was our energy balance equation. So again, this is our heat removal rate and this is our heat generation rate. Okay, let me rewrite this little bit in terms of our dimensionless variables. So I bring this T naught minus Ti on this side, and this CAI delta H by rho Cp, that is our delta T max, and then delta T max we can divide and we can write this left hand side in terms of theta, the dimensionless temperature rise, and K naught e raised to minus E by R T naught 1 minus XA into tau. What I want to do is to replace this XA also in terms of tau. So we can get that from our material balance. This is our material balance equation. We can write this material balance equation in terms of XA from our material balance equation in terms of tau, and then we will have a unique relationship between XA and tau. So if you do that, you will get this expression. Okay, fair enough. Is like theta is like k tau divided by 1 plus k tau. Only thing is T out, that T out is unknown. It is T out itself is in terms of theta. T out, this is T out is equal to Ti plus delta T max into theta. So this is a nonlinear equation in theta. What we are going to do is plot different, the left hand side and right hand side. When you have to solve equation, what we are saying, left hand side if we plot with respect to tau, right hand side if we plot with respect to tau, the point of intersection of the heat removal rate and the point of intersection of the heat generation rate, that will be our steady state value. Right, that's what we mean by solving. Maybe I'm going too fast, but the control is in your hand. You can pause the video anytime you want and make sure that you understood what I'm trying to say. Unless you are understanding, don't go forward. Don't just blindly see the lecture. Okay, so what we are going to do is plot this heat generation and heat removal rate as a function of theta in terms of tau, actually as a function of tau, and plot the point of intersection of the two functions. One function is the heat removal function, it's just theta, and the heat generation function, right? And find the steady state values of tau in the range 0.01 minutes to 20 minutes. Okay. What you can do again is you can resort to Excel and try to see how these things vary. So I have put this in Excel. You can do this as well. Look at this graph. This red curve is the heat generation curve, and the blue curve is the heat removal curve. So heat removed or heat generated in terms of theta, or tau if you like, in terms of tau actually. Sorry, it's in terms of theta. It is plotted with respect to theta for different values of tau. So tau here is 0.24. Now we can change these values of tau. So let's say we start with some value of tau. Let's say tau is equal to say 3.24. Right? Now you see this red curve and this blue curve intersect at 3 points. One here, one here, one here. If I reduce the value of tau, you see they intersect only here. They don't intersect here. If I increase value of tau to some very large value, you'll see what happens. They practically don't intersect here, they intersect only here. At any intermediate value, the tau heat generated curve and the heat removal curve, they intersect at 3 points. 3 points. And these are the 3 steady states that we get in our previous, like our previous graph. Now look at these 3 values of steady state. Okay. What I've done is I've just taken different values of tau and I have plotted them. And I'm just going to show you back, take you back into our PowerPoint. Okay. So here are some values. You see, when tau is very small, it intersects 3 points, one here, one here, one here. But if I reduce it even further, they will intersect only here. That means zero conversion, zero heat generation, only one steady state. At very low values of residence time, I have only one steady state, practically zero conversion, right? Let's go forward. Somewhere here, if tau is say 0.1 or 1, it intersects at 3 points, here, here, here. Tau equal to 0.1, let's plot that, let's look at that. Tau equal to 0.1, it intersects here, 0.0 practically, maybe something like this, theta equal to 0.6 sort of, and say 0.98 here. At 0.1, there are 3 intersection points, 0, practically 0, around 0.6, and close to 0.98, 0.99, 3 intersection points. So these are the 3 steady states that you get. At high residence time, they intersect only here, 100% conversion. You see, oops, sorry. High residence time, yeah, they intersect only one steady state, 100% conversion. Okay, look at these 3 steady states once again. Let's say my steady state value, let's put another color. Let's say the steady state value is another color, black. Let's put black. Blue is already there and red is already there. So this is one steady state. This is one more steady state. This is one more steady state. Look at this steady state first. Suppose in this steady state, the theta changes or residence time changes little bit. So let's say because of the dynamics, because of disturbances, the point shifts heat removal rate and the heat generation rate. Let's say this point tends to shift to the right. Theta is shifted to the right little bit. Theta is like dimensionless temperature. So there is a small disturbance in temperature. Now if it shifts to the right, what happens? The heat generation rate is more than heat removal rate. Temperature will continuously rise. Temperature will continuously rise means theta will increase. So if a small disturbance occurs, this point steady state, it was operating at steady state, but because of a small disturbance, it will now shift to this steady state. Why? Because heat generation is more than heat removal. If it shifts to the left little bit, if temperature falls little bit by say disturbance in temperature, inlet temperature or whatever, then the heat removed is more than the heat generated. this steady state, it was operating at steady state, but it will shift now to this steady state. That means this middle steady state is an unstable steady state. If I have to make my reactor operate at this steady state, I have to have very nice control strategy. Whereas look at this the ignition point. This is our ignition point and extinction point. If steady state, or if there is a temperature disturbance, if it shifts to the left, heat generation is more than heat removal. Temperature will rise, again it will shift back to this steady state. Or here, if it shifts to the right little bit, heat removed is more than heat generated, the steady state will shift, come back automatically to this extinction point. So these extinction points and ignition points, these are stable steady states. Now you see, as per your undergraduate course where you had thought of only isothermal reactions, you had thought CSTRs were so easy, well mixed reactor was so easy, concentration is same everywhere. Now you see all these complications come in because now reactions are exothermic. There is a dynamic or balance between the heat generation and heat removal that can give rise to multiple steady states. So deciding residence time in the reactor, deciding where I should operate my reactor, also depends on whether I have a stable steady state or an unstable steady state. Let's go forward. Understand all these things, then only go forward. So here is a small problem for you. Let's say there is a first order exothermic reaction K0 e raised to minus E by RT. Heat of reaction is delta H minus delta H. These are the values that we have taken. These are the values that we have taken. Now what I want you to do is imagine that there is a jacket as well, and the jacket, there is a coolant that is supplied. Coolant is at a temperature Tc. So we had looked at adiabatic first. These graphs were all for adiabatic when we had no heat removal from jacket. Now we are looking at a diabatic, means heat is allowed to be exchanged to the outside jacket, if you like. So cooling water is supplied and temperature inside the jacket is Tc, and we are assuming that this Tc is constant. Okay, again same thing I want you to do. I want to plot XA, write material balance, write enthalpy balance, and generate equations and write and calculate how the temperature and conversion changes with the residence time. Right? So I want you to write these equations and solve them for yourself. Take these values, you can solve for these values. Pause the video, do this exercise for yourself. Here is what you will find. Material balance, if you write, it is same as last time. Right? K, the only thing is K is now K naught exponent of minus E by RT naught. Enthalpy balance. Now what I have to write? Enthalpy in because of the flow, enthalpy generated by because of reaction, minus enthalpy removed by the jacket, in plus generated minus what is removed by the cooling medium must be equal to what is going out because of the flow. And again I can go through all this simplification and write an expression in terms of theta. Now you will see another parameter that is appearing. Another parameter that is appearing is this UA by V rho Cp. Look at this parameter. You might have studied this parameter in your heat transfer course. Look at this parameter, UA divided by V rho Cp, or V into rho is nothing but mass of liquid in that reactor, UA divided by mCp. You recollect this? Let me write the units, maybe then you will recall. U, heat transfer coefficient, watt per meter square Kelvin, area, meter square, mass, kgs, Cp, joules per kg Kelvin or kilocalories per kg Kelvin, whatever units are your favorite. Watts we can write as joules per second, right? And then joules we can cancel out. So UA by MCPs has units of second inverse. You may have recognized this in some other way. You may have seen this earlier in some other way. MCP by UA. Now do you recall from your unsteady state heat transfer course? MCP by UA is nothing but time constant for heat removal. Through the jacket. So I have one more parameter now. I have heat generation, I have rate of heat generation, and I have a rate of heat removal as well. And you see our expression, our earlier what we had seen in the previous class, A by V appears, surface area per unit volume. Higher the surface area, faster would be the surface area per unit volume, faster would be the heat removal rate, time constant will be lower. It responds very fast. Why? Because area per unit volume is, or area per unit mass if you like, is large. Okay, so that's why small reactors, laboratory reactors will be able to respond, will be able to transfer heat fast because surface area per unit volume is high. Real life plant scale reactors, surface area per unit volume or per unit mass is less. They are not as able to take out the heat. Okay, so make sure that you get this expression for yourself, derive it for yourself, right? Now again, what I want you to do is plot how theta varies with tau. So only problem now is it is nonlinear in theta as well as it is nonlinear in tau. Typically, if you take some value of theta, what we had done earlier, we had taken some value of theta and we have solved for tau because it became linear in tau. Now for one value of theta, you will get a quadratic in tau. You see tau is here also, tau is in the denominator also. So when you simplify, you will get a quadratic in tau. So solve that quadratic in tau, you will get two roots of tau. Both are possible because both are coming from this equation. So for every theta, you will have two values of tau. So plot these equations, so solve and plot these equations, plot the theta versus tau variation or xa versus tau variation or T out versus tau variation for yourself. Do this for yourself. Pause the video, do it for yourself. Only when you have done it, you can go forward. Here is what you will find. Temperature versus tau, residence time. Temperature on y-axis versus residence time on x-axis, or conversion on y-axis versus residence time. You see now, like earlier, we have now multiple steady states. At some value of residence time, let's say 1 minute, I have three possibilities. Let's put another color, otherwise it's confusing. Right. At say residence time of 1 minute, we could have temperature of say 299 Kelvin. We could have a temperature of 330 Kelvin. We could have a temperature of 400 Kelvin. Correspondingly, conversion could be 0, or it could be something like 30%, or it could be practically 100%, 99 point something. But at a particular temperature, if I want my reactor to operate at, let's say, 360 Kelvin, correspondingly, let's say 60% conversion, I could operate this reactor with multiple values of residence time. I could have a residence time of 0.08 minutes. I could have a residence time of 90 minutes. I could have a residence time of, let's say, 200 minutes. So you see, now there are multiple, for any conversion, I have multiple possible values of residence time. Right? You see, I could operate my reactor at this conversion, at say 80% conversion at this residence time, or this residence time, or this residence time. But somewhere I have a unique relationship between conversion and residence time, right? In this, so now I have to worry about which of these is a stable steady state, which of these is an unstable steady state, and correspondingly design my control strategy, correspondingly design my operating strategy for operating this particular reactor. And you see all these things change with respect to the properties, enthalpy of delta H, E by R, and so on and so forth. Let me just show you in terms of the Excel sheet. You see all these calculations you can do and plot these graphs for yourself. And same way we can change residence time, and we can have multiple values, multiple places where the heat removal rate and heat generation rate intersect each other. Do these calculations for yourself, only then you will be able to appreciate all these things. So you thought, well, mixed reactor is so easy to operate. Now you see all these complications: ignited steady state, extinguished steady state, stable steady state, unstable steady state. All these things you have to think about. Okay, so low residence time, we have behavior similar to earlier, right? This was our behavior similar to earlier. This part was similar to earlier. High residence time, temperature drops due to increased heat removal rate. So you see at higher and higher residence time, temperature drops because of removal. The heat removed is easier. So heat removal is faster and faster. So you see conversion drops in this high residence time. But then beyond this residence time, conversion again goes up. Why is that? Now because now residence time is more. Practically the temperature is practically not increased. Heat removal rate is so fast or so good that temperature has not increased. Now additional residence time will increase the conversion. So these different parts of this operating, different parts of this curve tell us different things about how we are operating our reactor, how we have designed our reactor. So again, you can plot these in terms of residence time. So you will have 3 for say tau equal to 0.02. You will have 3 steady states. Middle one will be unstable steady state, higher one and the lower one will be stable steady state. And you can see, you can plot these again. They are different now. Tau equal to 0.02, tau equal to 0.1, 1 and 12. These values are now different because heat is removed. You see, say tau equal to 0.1, we had let's say temperature was 350 Kelvin. Now in our earlier case, when tau equal to 0.1, we had theta equal to something like 0.5, 0.6. You can convert that into temperature and see for yourself what is the effect of heat removal rate through the jacket. Okay, one small point we need to still do: dynamic behavior. Dynamic behavior means how this concentration and temperature are changing with respect to time. So when you design a plant, when you operate your plant is not going to operate at steady state straight away. You are going to start your plant by taking some material inside, allowing reaction to happen, starting this flow rate coming in, going out, and then allowing it to come to steady state. So what we need to calculate is how the concentration in the reactor, Ca inside the reactor, and temperature inside the reactor, how they change with respect to time and how it approaches the steady state, right? So for example, if you plot with respect to time, just to give you an example, we may start a reaction at our inlet concentration. We may have everything inside equal to 2 kilomole per meter cube at the inlet concentration. So say 2 kilomole per meter cube. CA as a function of time, and we allow this reaction to happen. We start the inlet flow rate, we start the outlet flow rate, and we allow it to come to steady state. So it may come to some steady state value. So this is this is the dynamic behavior that we are talking about. Where is it important? Startup condition, plant startup. It is at zero time, we have put in the reactants, we have allowed reaction to take place. With respect to time, concentrations will change, temperature will change, it will come to steady state, hopefully. Okay, that word hopefully is what I am going to explain, or what you will see in your slides as you go along, or in your lecture as you go along. Okay. So this is very important in terms of how fast my plant approaches the steady state, whether it takes 1 hour to reach steady state, whether it takes 12 hours to reach steady state, or whether it takes 5 minutes to reach steady state. Obviously, the sooner it reaches steady state, better it is for our operational convenience. If it is going to require 12 hours, 24 hours for it to come to steady state, then plant personnel, you have to monitor the plant very carefully, make sure that conditions are safe. Right? So that is why we are studying this dynamic behavior, how from an initial value, how the concentration in the reactor, conversion in the reactor, and temperature change with respect to time, and how they approach the steady state. We talked about multiple steady states, which one is stable steady state, which one is unstable steady state, but we have not talked about how long it takes or how it approaches that steady state. That is what we are doing now, dynamic behavior. So let's say, first of all, I want you to derive equations for how CA and T change with respect to time. So now you have to write unsteady state material balance and unsteady state energy balance. Do this for yourself. Pause the video, do it for yourself, derive these equations. Only when you have derived, then only go forward. It's okay even if you get a wrong answer, or even if your derivation is wrong a little bit. Right? So solution is write unsteady state material and energy balance. We can take same data as the previous problem. The values of energy of activation, delta H, inlet concentration, inlet temperature, all those flow rates, you can take the same as the previous value, previous problem. Okay, unsteady state material balance, when we want to write, what do we write? Accumulation inside the reactor is what comes in minus what goes out minus what is reacted. Material balance, this is something that we have done in our undergraduate course. First course that we do in chemical engineering is material balance. So V into Ca at T plus delta T, we are writing now a balance with respect to time. Time T plus delta T minus at time T, that's the accumulation. What comes in? Now flow rate into concentration, that is what is coming in, that is the rate at which it comes in. How much it come, how many kilomoles come in? Rate multiplied by delta T. F into Ca, rate at which it goes out, into delta T is the total moles gone out. Kca is the rate in terms of kilomoles per unit time per unit volume, multiplied by volume is tells you what is the rate kilomoles per second reacting, multiplied by delta T tells you how many kilomoles have reacted, how many moles have reacted. Divide throughout by delta T, take limit as delta T tending to 0, you will get this expression. Get this for yourself, don't go forward unless you get this. We can write in terms of tau, V by F we can write. Remember, this K is our K naught e raised to minus E by RT. Same way energy balance we can write. Enthalpy at any time T plus delta T minus enthalpy at time T, that's the accumulation of enthalpy. What comes in, what is generated, what goes out by way of flow, and what goes out by way of jacket, removed through the jacket by the coolant that is there. So simplify, you will get this expression. So I need to solve these two equations. Let's rub out all these things so that it is nice and clean. I need to solve these two equations simultaneously. These two differential equations we need to solve. How do we solve? What methods do you know of solving differential equations? If you don't know any, go back to your undergraduate course, numerical analysis, or some course where you studied maths course, some course where you studied how to solve differential equations, and solve these differential equations for yourself. One of the ways could be Euler's method, explicit method. I wanted to solve this numerically. Of course, analytical solution is not possible. Solve these equations numerically. You can do MATLAB or something like that if you know already. I want you to solve these with respect to the initial condition. What is the initial condition? At t equal to 0, Ca is our Ca initial and t is t initial. And I want to do three cases. Case 1, tau is 100 minutes, Ca initial is 0.2, T initial is 325. Now we are going to keep this Ca initial same and just change tau from 100 to 72 to 70. Okay, 100, 72, 70. 100, 72, 70. Here is where we are. 100. These are the three dynamic behavior I am requesting you to see. 100, residence time is 100. Means this is one case 1, 100. Case 2, 20, 30, 40, 50, 60, 70. Case 2 is here. Case 3 is very close to it, 70 and 72. So we are talking about this much variation in residence time, 100, 72 and 70. And at that residence time, we have, mind you, we have only one value of steady state. It is not that there are multiple steady state. It is only one steady state that is possible. Okay. 100, 72 and 70. They are all here. 100, 72 and 70. It is this part that we are looking at. There is only one steady state. We don't have multiple steady states in this range of residence time. But we'll see how the dynamic behavior looks like. Right? So solve these three cases. Solve these for yourself. Pause the video. Only when you have done it, you can go and continue the lecture. Here is what you will find. Look at this case 1. Tau is 100. We start with initial temperature 325 Kelvin. It reduces to 300 Kelvin, goes up and reaches a steady state. It has reached steady state by this time, something like 300 minutes. In terms of conversion, we started, initial concentration was 0.2, which means we had something like 95% conversion. It reduced and reached a steady state. Some oscillations are there. It reached a steady state somewhere here, 300 minutes, 300, 350 minutes, 400 minutes, something like that. Okay. Another way of looking at it is plot in terms of conversion versus temperature. We started here 325 Kelvin and let's say 90% conversion. Conversion increased slightly, reduced, temperature reduced. It followed this trajectory, temperature versus time followed this trajectory and reached this steady state. So this is how the temperature versus conversion trajectory changed when residence time was 100 minutes. It started here, it came to this steady state. And then once it is at steady state, it remained at that steady state. That's why a constant temperature versus time, constant conversion versus time, steady state. Steady state, beyond 300, beyond 400 minutes. This is the conversion versus temperature trajectory. How the reactor approached the steady state. Conversion versus temperature plane, if you like, phase diagram, if you like. Let's change residence time. Tau equal to 72 minutes. Any guesses? pause the video, do it for yourself, see the behavior for yourself. Only once you are get the even only when you get the answer, do it for you can go forward. This is how the temperature versus time will look like for 72 minutes. We start with 325, temperature goes down to 300, goes up to 315, goes down, goes up, goes down, goes up, goes down, goes up, and so on. Oscillatory behavior. But you see, these oscillations are damping out. These oscillations are reducing. The peak temperature is reducing, the minimum temperature is increasing, and it will approach a steady state. In terms of conversion versus time, conversion reduces, goes up, reduces, goes up, reduces, goes up. The oscillations are dying out. So it is approaching steady state. It will approach some steady state. If I continue this analysis, if I continue solving the equations for longer and longer time, it will approach a steady state. Look at the time, 1000 minutes, it has still not reached steady state. 1000 minutes means like 16 hours, 17 hours. Whereas here, in first case, it approached steady state within 4 or 5 hours. Just changing the residence time from 100 minutes to 72 minutes. Oscillations are there, and these oscillations slowly dampen out, and they reach a steady state. You reach a steady state. In terms of phase plane diagram, if you want conversion versus temperature, we start here, and you see oscillations. Oscillations are characterized by this behavior. You see, it will approach some value. It will reduce, move forward, and slowly it will approach a steady state. Contrast this behavior with respect to this behavior. So fast it was approaching steady state. Now it is oscillating and approaching steady state. That's why process control becomes important. What kind of controller I have to control these oscillations? You thought process control was such a non-required subject or such an easy subject. Now you see all these dynamics come into picture. Reduce the residence time little bit from 72 minutes to 70 minutes. What do you expect? Solve, you will see for yourself. See? Temperature versus time reduces, goes up, reduces, goes up, reduces, goes up, reduces, goes up. These are oscillatory behavior. It never reaches steady state. It continues to oscillate between 333 Kelvin and 300 Kelvin. In terms of conversion, it oscillates between 99% conversion and 40% conversion, 41-42% conversion. Would you want to operate a reactor that oscillates all the time between 40% conversion and 99% conversion? And the time period of oscillation, you see, is something like 200 minutes. These are not fast oscillation, these are slow oscillation. In terms of temperature versus conversion, we start from here, but you will never reach a steady state. It continuously goes around this loop. It's called as limit cycle. Don't worry about the name. See in terms of what is the implication for our reactor. Reactor oscillates all the time. Now process control becomes even more important. How do I dampen out these oscillations and make sure that reactor operates safely? Otherwise, we will have a reactor which is oscillating, temperature is changing by 40 Kelvin, 50 Kelvin, 50 degrees centigrade. 40 degrees centigrade. Conversion is jumping, changing by from 40% to 90%. Every cyclical behavior. It is just oscillating. It is not reaching a steady state. Only change we have made is residence time. 100 minutes, we have made 70 minutes. That's how this part is called as real life reactors. Just to give you some more material to read, some problems. So if you read Fogler's book, 4th edition, we are on chapter 8 and 9. You can solve these two problems, problem number 816, problem number 817. There is also a solved example 9.5 and 9.9. Problem 9.9, P99 is an unsolved problem. Solved example is 9-5. If you are referring to 5th edition, we are on chapter 12 and 13 in the 5th edition. Dynamic behavior and steady state, but exothermic and adiabatic and diabatic reactors. So these are the considerations that go on into a real life well mixed reactor. And you thought well mixed reactor is so easy to understand. It has all these complications because there is an interplay between heat generation, heat removal, and it can lead to very complex behavior, multiple steady states, stable steady state, unstable steady state, dynamic behavior. Either it will reach a steady state, slowly oscillate and reach, or it will keep on oscillating, or it will diverge. Means temperature will go to very large values, like a runaway kind of a reaction. So you need to, when you design a reactor, you need to analyze all these conditions a priori, prior to selecting a residence time, prior to designing. Right? What diameter, what height, what temperature, what agitation, what jacket, area, all those things you need to design and address in your design, that make sure that we get into a steady state very quickly. Make sure we don't have dynamic behavior, or the dynamic behavior is as limited and it reaches a steady state very quickly. All these things have to be calculated and built into your design. Then only your design is useful in an industrial context. We are not solving problems for the sake of solving problems. It is not that we solve these problems and get marks in an examination and finished. We never have to worry about it. It's not that. All these considerations you will have to use when you start designing reactors after your graduation. Right? All these considerations you have to take into account if your design is to be useful and stable and safe, most important. Okay? So we'll stop this lecture here. Make sure you have understood, you have derived everything for yourself, and and solved and understood all these concepts.